Thank you. So my name is Gábor Rácz. I'm a PhD student at Eötvös Loránd University. I'm a PhD student of Eötvös. And I'm working with cosmological simulations also with István Szapudi and István Csabai. So I will start with a short introduction about the standard cosmological model and the large-scale structure of the universe. And after that I will talk about new simulation methods. So if you want to do cosmology, we should start with general relativity and the Einstein equations. Yes, so these equations connect the stress-energy tensor of the matter with the geometry of the space-time. And the cosmological principle says that the universe in large scales are homogenic and isotropic, so we should use a homogenic and isotropic metric. This is a Friedmann-Robertson-Walker metric. If we put this metric into the Einstein's equations, we get these two independent equations. These are the Friedmann equations. Basically, these are describing the expansion of the universe, so the scale factor is the only time-dependent stuff in this. And this shows basically how big is the universe at a given time. So, standard model says that nearly 4% of the density of the universe comes from atoms or baryonic matter. 23% is dark matter, and the rest of is dark energy. So the standard cosmological model is around the CDM model, and the lambda means that there is a cosmological constant in this model, and the CDM comes from the cold dark matter. And this model has 6 independent parameters, and it fits well with the measurements. So you can see this in its expansion history from this model. So these are two slices from the parameter space of this model, and we see that so these are the measurements, and these measurement points were the small volume in this parameter space basically. For us, the most important is the cosmic microwave background and the clusters of galaxies basically. So let's start with the cosmic microwave background. So this is a picture of it seen by the Planck telescope. This is a temperature map. It's a full sky temperature map from the cosmic microwave background. And from this temperature map, we can reconstruct the density field. So this is a picture from the very early universe. This time was nearly 400,000 years old universe. So the fluctuations in density fields are very small, 10 to the -5, the relative fluctuations. So these are quite small. And if we look a bit closer and we reconstruct so we look at the galaxy distribution in the nearby universe, we see this picture. So these points are basically galaxies, and you can see big voids, walls, clusters of galaxies, superclusters. And we can reconstruct here also the density field, and the relative fluctuations here is 10 to the 6th. So there are big fluctuations today. So what is the connection between these two? And I will answer it later. So these are nice pictures, but we want to do some statistics. So there are basically two functions are used for this, but there are many others. The first is a two-point correlation function, and the second is the power spectrum. These are basically shows how big are the fluctuations at given scale or wave number. So what is the connection between these two measurements? And the connection basically is the gravity. So at the early times the fluctuations were small, and there was fluctuation, so the gravitational instability formed these structures from these big structures basically from the small fluctuations that we see in the CMB. So we want to calculate the matter distribution as a function of time basically. So at early time, so the initial conditions come from the cosmic microwave background power spectrum. And at the early times we can use the linear perturbation theory because the fluctuations are quite small. But in the later times the structures will be, or the fluctuations will be too large for the perturbation theory, so we have no choice but to use cosmological simulations. So what are these cosmological simulations? They are basically n-body simulations with dark matter or dark n-baryonic matter. We work only with Newtonian gravity, and we have an expanding periodic box. The number of particles can be very large, so the biggest is 10 to the 12th. So it's quite large, and the initial conditions come from the cosmic microwave background power spectrum and from perturbation theory. So, for example, this is a slice from an initial condition. So we have it's a nearly 2 gigaparsec size box, and it has 343 million particles. And this is the initial conditions. We use the Planck Landau-Sigian parameters for generate this. And if we run this simulation, we get this. So this is the output of the simulation. This is nowadays, so more than 13 billion years later than the first picture. And we see also these voids, these walls, clusters, basically everything what we see in the measurements. So the theory works basically, but there are difficulties with these cosmological simulations. We have high performance computing needs for the force calculation. We have very large number of particles and everything interacts with everything, so it can be hard. There is another difficulty that if I want to use very fine mass resolution, for example, I want to see galaxy formation in this big expanding universe, the number of particles can be very large, so we have also high memory requirements. So that's another problem. And there are two minor difficulties. That first, the direction in the simulation box are not equivalent, so we have a periodic box, there are distinct directions. So we need to use large volumes if we want good results. So this can cause problems if we use a small box. And the fourth minor difficulty that the measurements are done in the sky and that is spherical, and we have a periodic box, so we have two different geometry basically, and one can work on this, everybody doing this, but it would be nice that we would have the same format of in the simulations and from the measurements. So if we are only interested in small scale, so for example galaxy formation, then for the first two problems we could use zoom-in simulations. So the main idea is to run simulations with different spatial resolutions. So it has two main steps. The first is that the parent simulation run with low mass resolution and with the large simulation volume to minimize the effect of the periodic box. And after the simulation is finished, we choose a small volume of interest where we interested in the fine structure for example, galaxies or something like that. And if we choose this, we run a second simulation with spatially varying resolution with the same simulation volume. So we have a big simulation box. The large portion of it has a low resolution, and we have a small volume with very fine resolution. So this is the basic idea, and there are only a few nested cubic volumes with the same center in this case. So in this case, we have smaller number of particles. So we do not have so much high performance computing need, and we do not need such a high memory. And this is but we also in this cubic geometry. So we have a new method for these zoom-in simulations, and for this we use stereographic projection. So the stereographic projection is a well-known bijective geometrical transformation between a sphere and a plane. So in one dimension it basically looks like this. So we map this sphere. So we have a coordinating sphere of, for example, this omega, and we project this into this straight line in one dimension, basically. And the inverse transformation is from this straight line, we project this point back to the circle. So this is the one-dimensional case. It's easy to see that this is the inverse transformation is basically compactification. So we map this infinite straight line into a finite circle. So, but we want to do cosmological simulations, and we have 3 spatial dimensions. So we want to do this in 3 dimensions, and luckily it's easiest. It's easy, basically as easy as in 1 dimension. So if you use a spherical coordinate system, only the radial coordinate is transformed. So theta and phi are untouched, and we do compactification in the radial coordinate. And we use this transformation to generate initial conditions. So how we do this? We get a big, quite large periodic initial conditions from Angelizzi or Tulapiti. These are codes for generating periodic initial conditions. We choose the volume of interest in these ICs, and we use a large spherical region from this initial condition, and we transform this spherical region into the surface of a 4-dimensional sphere. And in this sphere, we binge the data. So the 4-dimensional sphere has the surface of the 4-dimensional sphere is a 3-dimensional object. So we have 3 coordinates: omega, theta, and phi, and we use heel peaks for binning in the theta phi, and we use a simple equivalent binning in omega. The particles are united in each bin. And after this, we use stereographic projection to transform these coordinates back to the normal space, to the Cartesian coordinate systems. So this is our input. In this case, we have, this is the same what I showed you before, so it has more than 300 million particles. And after we do this transformation, this is what we get. spherical initial, we got a spherical initial conditions with constant angular and decreasing radial resolution in radial direction. So in the center we have very fine resolution, and as we go outwards, the resolution breaks down, so it becomes worse. And at the edges of this, we have so bad resolution that we reach, in the ideal case, the homogeneity scale of the universe. So at here we're hoping that we will not see anything. So, and we got initial conditions, so we should run n-body simulations. I forgot to mention that in this initial condition we have only 1.5 million particles, so we reduce the number of particles. So we should run n-body simulations. We use only gravity, and we should use non-periodic boundary conditions, so we do not want to use the periodic boundary conditions, and the expansion rate are governed by the Friedmann equations, and the forces for these, so we have a spherical boundary conditions, and the forces for this can be calculated by the Newton's shell theorem. So, and we assume that the density field is always homogeneous outside. We can do this because we have so bad resolution in here, so we cannot distinguish the homogeneous and the inhomogeneous case. So there are no, so yes. Okay, so this is how we calculate the forces. So think about that the whole universe is exactly homogeneous. In co-moving coordinates, one particle in this case feels zero force. So we have this is our simulation volume, this blue circle, and these particles should feel zero force. So we divide the four separate regions, our model universe. So outside this is a white region. If you use Newton's shell theorem, we easily see that force coming from this white region is zero. And also this part, we call it U. If you also use the Newton's shell theorem, we see that force from this U is zero. So we have this part, C, and this part I. And because the particles feel zero force, that means that this force should be minus, so Fc is equals minus Fi in this case, and we can calculate the force easily from what comes from here. So you get this force from Fc, and because we use homogeneous, so our boundary condition basically that outside is everything is homogeneous. So if there are structures in here, the force will be same. So this will be the force in the simulations. So I write code to demonstrate this method. It is a cosmological anomaly code. It's dark matter only, and this is a demonstration. So I use the naive n-squared force calculations, and I use this spherical boundary conditions, and it parallelizes OpenMP and QDA. And this is the result. So I started from these initial conditions, and there are periodic simulations too. So so we can see that we see the same structures in the volume of interest. So this is a big supercluster, and we see this also here. So it's pretty clearly works, and these are nice pictures, but we want to compare these. So this is a map of a shell from these simulations. This is from a periodic simulation, and this is from our stereographic simulation, and this is a spherical power spectrum. And what we see, we got the same spherical power spectrum basically for the two at 50 megaparsecs, and it is true for 100 megaparsec, 200 megaparsec, and even for 300 megaparsecs. So, but in the left-hand side we used 343 million particles, and in the right-hand side we used just 1.5 million particles. And the difference is basically you need a supercomputer to do this, but with even this n-squared algorithm with CUDA parallelization, you can run this in your laptop in a few hours basically. So, summary, with this algorithm we can reproduce a mass distribution in a spherical geometry with a smaller number of particles, and easier to run simulation in larger volume because of the compactification. And I didn't mention it, but we can calculate fastly redshift cones with this simulation, and easier the comparison with measurements. So we have the same geometry basically. So the sky is spherical and our simulation is also, so we don't have to convert these periodic simulations into a spherical thing or something like that. And in the future we're planning a full Hubble volume simulation and to write a better initial condition generation code. So thank you.
Questions? No? Lena?
Can you expand the volume of the simulation using these techniques? What is the final size you can use?
So these simulations were about nearly 2 gigaparsecs in diameter. And so the basic limitation is that this example code is used n-squared for calculation, so it not scales very well. But we are hoping that after some further optimization, we can run a full Hubble volume simulation. And if we choose well the parameters, we can reproduce such statistically, of course, the large-scale measurements. So we don't see very far away with these measurements. So we don't need to simulate that far parts of the universe. And we can also use this for light propagation calculations, so the photons come from here and calculate how they go into the observer, basically. So theoretically it can be used for a big Hubble scale situation.
I have another question regarding this plot. Why are there small wiggles in the
So this is just a small demonstration. So this is because there are structures in here, and we not really reached the homogeneity scale. So we also need much bigger volume, but so basically these are errors. But they were worse for not errors, but
The back reaction.
no, it's not back reaction. If you see the diameter of this, it will be the same. The average diameter will be the same, so you don't see back reaction. Normal back reaction.
Okay. Let's thank Gábor again.